Right now, inside the device in your hand, something is switching on and off billions of times every second. It has no levers, no moving parts, no sound at all. It is smaller than a virus, and there are billions of them sitting side by side on a sliver of silicon. This is the tiny switch that quietly runs the modern world. Let us slice one open and watch how a transistor turns a whisper of voltage into a clean, perfect yes or no. A transistor is a switch, but not the kind on your wall. There is nothing to flip and nothing to wear out. Instead, it controls electricity with electricity. A small voltage at one terminal decides whether a current may flow between two others. Think of a faucet where, instead of a hand turning the handle, an invisible electric field opens and closes the tap. That is the whole trick. Everything else is just a clever way of building that faucet out of solid rock. To build it, we need a strange material, a semiconductor. Most things are clear about electricity. Copper conducts, it lets current pour straight through. Glass insulates, it blocks current cold. Silicon sits in between, undecided. On its own, pure silicon barely conducts at all. Its electrons are locked into neat bonds, with almost none to spare. But that indecision is its gift. Because silicon can be coaxed either way, we can build a material that conducts only when we tell it to. We change silicon by poisoning it, on purpose. This is called doping. Mix in a trace of phosphorus, and you add spare electrons that drift freely. We call this negative, or N-type, silicon. Mix in a trace of boron instead, and you create tiny gaps where electrons are missing. We call those gaps holes, and this is positive, or P-type, silicon. A few stray atoms per million is enough. With doping, we paint regions that overflow with electrons and regions that crave them. Now we lay out the parts. In a block of P-type silicon, we place two pools of N-type, a small gap apart. One pool is the source, where electrons begin. The other is the drain, where they want to go. Between them lies the gap, which we call the channel. Above the channel, separated by a whisper-thin layer of glass, sits a metal plate called the gate. The gate touches nothing below it. It only hovers, ready to cast an invisible field downward. With no voltage on the gate, the transistor is off. The source and the drain are two islands of N-type, surrounded by a sea of P-type. Between them, the holes form a wall. An electron leaving the source meets that wall and stops. No path exists across the channel, so no current flows. The switch is open. This is a clean, settled zero, holding firm with nothing moving and almost no power spent. It will wait patiently like this for years. Now we put a small positive voltage on the gate. Remember, the gate sits just above the channel, separated by that thin sheet of glass. Like charges repel and opposites attract, so the positive plate pushes the holes away and pulls electrons up toward the surface. The free electrons hiding in the silicon rush upward and gather in a thin layer right beneath the gate. In an instant, the wall dissolves. A fresh bridge of electrons forms across the gap, joining source to drain. With that bridge in place, the channel is open. Now electrons stream out of the source, across the new layer and into the drain. Current flows. The switch is closed, a solid ringing one, and here is the beautiful part. The gate did this without drawing any current itself. It only held up a field, like a magnet held near a compass needle. A tiny, nearly free voltage now governs a much larger flow. Lift the voltage away, and the bridge simply vanishes again. This gives us two powers at once. First, a switch. Gate high means on, gate low means off, the ones and zeros that all computing is built upon. Second, an amplifier. Nudge the gate a little, and the current through the channel swings a lot. A weak signal coming in becomes a strong signal going out. The same small stone shaped two ways. Radios lean on the amplifier. Computers lean on the switch. Both are this one humble device doing its quiet job. Alone, one transistor is just a valve. But wire them together with the outputs of some feeding the gates of others, and they begin to reason. A few make a logic gate that can decide and or not. Millions make memory that can remember. Billions, etched onto a chip the size of a fingernail, Make a processor that adds, sorts, and conjures the screen you are reading right now. Every thought your phone has is built from this single move, repeated. And the smaller we make them, the better they get. A shorter channel means electrons cross it faster, so the switch flips quicker. A tinier transistor draws less power and lets more of them fit in the same space. This is the race that has driven computing for 60 years. Shrink the switch, double the count, and watch the whole machine grow brighter. We are now near the limits, building channels just a few dozen atoms wide, where the rules of physics push back. So let us trace it once more. We start with silicon, the undecided middle ground. We dope it, making N-type pools inside a P-type body. We lay down a source, a drain, and a hovering gate above the channel. With no gate voltage, the holes wall off the path, and the switch sits off. Add a small voltage, and electrons rush up to form a bridge, so current flows and the switch turns on. One valve, no moving parts, repeated 1 billion times. A whisper of voltage, a bridge of electrons, a perfect yes or no. The next time your screen lights up, remember the billions of silent switches working beneath it, each one slicing the world into ones and zeros. That is the transistor. Thanks for watching The Cutaway.